So what good stuff are we covering today?
The more of the vector stuff that we were doing last night.
Okay.
So could we start with the direction angle thing again? Because I didn't quite understand that.
Yeah, the direction angle is the angle that they make with the x-axis.
Okay.
Hold on a moment. I was just looking at that. Let's see. We're not on to parametric equations yet, right?
Not yet.
All right. A precise way to specify the direction of a vector is to state its direction angle. And that's the angle that the vector makes with a positive x-axis. Okay? So, if you know the magnitude of the vector, let's say we have a vector like this, and it is 8 at an angle of, we don't know. Hold on a moment. I'm looking at this example in the book here.
Okay.
The best, in other words, as long as we know the components, we can figure out the direction angle. If we know x and y, because that angle, theta, is equal to inverse tan of y over x. Now, do you have a specific problem? I mean, there's an example in the book. Find the direction angle of each vector. You want to go through one of those?
Yeah, sure.
All right. Let's find the direction angle of this vector. Well, it's actually pretty straightforward. That vector is the vector whose, if we complete the triangle, this has to be 3, that has to be 2. Now, all right, they make this more harder than they should. In other words, they have a rather complicated method of finding the direction angle. Let's see. They say that this vector has to equal the magnitude of the vector times the cosine of the angle that we're looking for. And the other has to be the magnitude of the vector times the sine of the angle we're looking for. Well, notice that that's the same thing that I've written with this picture, only it's much easier with the picture to just take the inverse tan of 2 over 3 rather than to go through this long complicated thing. But notice it's the same thing because the magnitude of u is this measurement right there. In other words, the magnitude of u is root 13. Okay? So the x-coordinate, which we know to be 3, has to equal root 13 times the cosine of theta. Or I can say that 3 has to equal root 13 cosine of theta. Do the algebra, and theta ends up being the inverse cosine of 3 divided by root 13. and that is 33.69 degrees. Do you have your calculator?
Yeah, I got it.
Do the inverse tan of 2/3. Let's see if we get that same exact answer. We should.
Um, 33.69.
Yeah. So why are they making us do this by such a hard method when there's an easy way to do it? In other words, whenever I suppose you could make the problem more difficult such that you might need this more difficult definition. But quite frankly, when they give you a vector that's just two coordinates, it's the inverse tan of that 2/3, y/x. Now,
would it be like that in the other quadrants?
No, here's how you do it. And this is the best way I've ever heard. Theta is equal to the inverse tan of y/x as long as x is positive. It's equal to the inverse tan of y/x plus pi if x is negative. Now, look at that closely. You don't get too many definitions that way. In other words, it's not saying you add pi if y/x is negative. The only thing we care about is the denominator. Okay? So, let's figure out the following one. The vector is v equals -2, -5. Well, that's right there. And we're looking for that direction angle. Well, if I use my definition, it would be the inverse tan of -5/-2, and since the denominator is less than 0, I'm going to add pi to that answer. What's the inverse tan of 5/2?
68.19.
So it's 68.19 plus 180, which is pi. That puts it in the proper quadrants. 248.19. Now, the other way to do that, the harder way as far as I'm concerned, I have yet to see the application where this other definition is better, but let's look at the other definition. This vector, and I'm going to erase this, must be equal to the vector where I have the magnitude of v times the cosine of theta being equal to the x-coordinate, and I have the magnitude of v times the sine of theta equals the y-coordinate. Which means, well, I know what the magnitude of v is. What's the magnitude of v?
The Pythagorean theorem.
What is it precisely? What's the magnitude of v?
So that'd be 4 plus 25 square root of 29.
Correct. Times the cosine of theta, square root of 29 times the sine of theta. And now I can make things equivalent. In other words, since this vector is equal to this vector, then cosine, square root of 29 cosine of theta must be equal to -2. So I solved that equation. Minus 2 has to equal this x coordinate right there, which makes minus 2 over root 29 equal cosine of theta. If you take the inverse tan of that, or the inverse cosine of that, what do you get?
You say the inverse cosine?
Yeah, interesting. We're going to get a second quadrant angle here.
Um, 111.8.
Yeah. Hold on a moment. I'm looking in their book. They've got minus 2 equals root 29 cosine of our angle. And they solve for b, but they subtract that from 360 without explanation. So now it gets even more mysterious as to why we're using this method, because my method worked much better. There's no vector that you cannot determine its direction angle using my method, and my method works perfect, whereas this doesn't quite. What'd you get for theta in this?
111.8.
And that's not theta, that's theta. But the way you get this number here is by subtracting that from 360. But there's no explanation as to why we would do that, why we would subtract it from 360. Because they see that beta is in the third quadrant. So if our angle is in the third quadrant, we have to subtract it from 360, the answer we got, which is kind of similar to what we have to do with my definition. But gosh, my definition is so much simpler. I say you go with my definition and you forget this harder method. The harder method makes no sense at all, whereas my definition, theta, is the inverse tan of y over x, or inverse tan of y over x plus pi, depending on what x is. This is if x is greater than 0. That's if x is less than 0. What if x is 0? What's theta going to be?
Infinity? Or would
it would either be 90. In other words, if x is 0, then we're looking at a vector that has no x direction, which means it's either this vector or it's this vector. You with me?
Yeah.
Okay, well, if it's this vector, y is going to be positive. So you would know that it's 90 degrees if y is positive, the answer. And you would know that it is 270 degrees if y is negative. So this definition for the direction angle is far simpler than theirs, and I think it works in all situations. All right. Do you have a textbook by Demaney, Waits, Foley, and Kennedy, a pre-calc? Figure out if we're using the same book.
It's like the title is just like Precalculus, Graphing Numerical Algebraic.
That's what my title is also, only mine has the authors at the top, Demaney, Waits, Foley, and Kennedy. It's probably yours.
Yeah, it's the same.
Okay, your vectors are section 6.1?
Yeah.
Okay. What other problems do you have? We can find direction angles now.
Yeah.
We can even find angles between vectors because we have a formula for that. That's pretty complicated, and in fact more complicated than it needs to be, because you'll notice that I have another way of figuring direction between two vectors. If I give you that vector and I give you this vector, well, I can figure out that direction angle, right, using my formula I just gave you. And I can figure out that direction using the formula I just gave you. So the angle between them would be the difference of those two angles. That's the simple way to do it. The hard way is by their formula. The cosine of theta equals u dot v divided by the magnitude of u times the magnitude of v. This is the official definition of the angle between two vectors. Easy enough. It's easy enough to take the dot product and the magnitudes. But we could also do it doing the way we just did. In other words, find each's direction angle and subtract them.
Okay.
Want to do a problem of finding the angle between vectors?
Yeah, sure.
Okay. Find the angle between these two vectors. We may have done this yesterday. I don't know, but if we did it, I did it, not you. So let's see if you can do it.
Okay.
There's two ways to do it. You could find the direction angle between the x-axis and u. Same thing between the x-axis and v. Subtract those two angles and you have the angle between them. Do it by the harder method. What's the formula? Cosine of theta equals, theta being the angle between the two of them?
Yeah, it's u dot v over magnitude u magnitude v.
Okay, let's fill in those. What's u dot v?
So is that 2 times 2, or 2 times negative 2 plus 3 times 5?
Yes.
Okay. So that'll be 4 plus 15, so 19.
Okay, it's 2 times negative 2, so it's minus 4 plus
negative.
15. So it's 11.
Okay.
What's the magnitude of u?
That's that root 13.
And the magnitude of v?
Root 29.
So theta is equal to the inverse cosine of that number. 11 over root 13 times root 29. That's one way to do it. Go ahead and come up with that answer.
Okay. So in my calculator, would I have to put like parentheses around the 13 and the 29?
Yeah, that's kind of hard to do in a calculator, isn't it? Because there's so many parentheses involved. Yeah, you would need to say inverse cosine of parentheses 11 divided by the quantity square root of 13 times the square root of 29. Each of those taken to the 1/2 power, in other words.
It's 55.49.
Okay. Now, just so you fully understand this problem, let's have you do it the other way also.
Okay.
What's the direction angle of U?
Inverse tangent 3/2, right?
Correct. What is that?
56.3.
What is the direction angle of V?
Negative 68.
Hold on. It's first of all, it's the inverse tan of 5 over negative 2, right?
Yeah.
Since the bottom is negative, we have to add pi to that.
Oh, right. So we would add 180 then?
Uh-huh. What's that?
Okay, so that's 111.8.
Notice the difference in those two angles.
Huh. Okay.
So again, it's, to me, certainly using your calculator, it's easier to do those two and subtract the angles than it is to do this in your calculator. Merely because that's really, and you're always going to have something that looks like this. You're always going to have the inverse cosine of a number divided by a square root of a number times the square root of another number. So that's always going to be problematic to get into your calculator properly. Whereas this method here, I think it works 100% of the time quite easily. The only thing is you have to remember that if your denominator is negative, you have to add 180, regardless of your numerator. It does not matter if this is a negative 5 or not. As long as x is negative, you add 180.
Okay.
It's not if the argument of the tangent is negative. It's only the denominator. I think this is the way I would do all of these problems.
Okay.
What makes two vectors perpendicular to one another or orthogonal? Orthogonal?
That one, they're like at a like when they're perpendicular.
Yeah. In other words, if I want to know if these two vectors, if that's a 90-degree angle or not, what has to be true if that's a 90-degree angle?
I'm not sure.
The dot products have to be 0.
Oh.
In other words, if I took the dot product of these two vectors, I don't get 0. I get 11. If these two vectors were perpendicular to one another, the dot product would be 0. And you'll notice by that harder method, if the dot product is 0, the numerator is 0, and the inverse cosine of 0 is 90 degrees.
Okay.
But the key thing is if the dot product of two vectors, if it's 0, those two vectors are orthogonal to one another. Let's talk for a moment about projecting one vector onto another.
Okay.
I don't really want to talk about this today because I haven't totally convinced myself how it works yet. But if it's something you're going to cover on the test, I want to be prepared to talk about it. So if it's something you're going to want to talk about before you take your final, I'll bone up on it.
Okay.
At least to the point where I can understand their example. Some of these vectors are awfully hard conceptually to understand. They're problems of a sled pointing downhill at a certain angle and finding what force is needed to keep it from sliding down the hill. Problems like that can be solved projecting one vector onto another. But again, I'm not even convinced that, yeah, I guess I am convinced that that's probably the way to go. Let's put that off to our next section, and our next session I will understand that problem that's in the book at least enough so I can explain it to you.
Sure.
How about parametric equations and motion? Are you not there yet, or?
Yeah, we are, but yeah, I need help with those things too.
Let's talk about those. Let me give you an example of why parametric equations are good. If I throw a ball at a 45-degree angle, it follows a parabolic path on an XY coordinate plane. Okay? So that if you give me the X coordinate, I can give you the Y coordinate. So I always know exactly where it's at on this path. However, what I do not know is when it is there. If I want that information, I would define this as two parametric equations and give a domain for t being time. In other words, if I know things like the speed that I release the ball at, and I have parametric equations, well then I'll know exactly where it is on this path at any time after 0. So parametric equations, I've always kind of taught them that they're no different than the XY equations, but they really are. They have more information. You're essentially taking an XY equation and adding a variable and making two equations out of it. So let's talk about a couple of parametric equations.
Okay.
And you almost always put a domain on time, or whatever the variable is. Just because it's t doesn't mean it has to be time. If it were time, it clearly wouldn't be able to go to negative infinity. So in this particular case, t is just some third variable. Okay?
Okay.
How do you eliminate the parameter? In other words, let's say I want to take these two parametric equations and restate it as an XY equation. Probably the most basic thing you can do with parametric equations. I mean, you really want to know how to eliminate the parameter. So let's go over that for a couple of these problems.
Sure.
Almost certainly you're going to have to do that on the test. Eliminate the parameter. How can I combine these two things so that I don't have t anymore and I have merely an equation in x and y? Solve each equation for t.
Okay.
What's t equal to up here?
be
Be 1 minus x all over 2.
Okay.
Okay, just doing the algebra. What's t down here in the y equation?
That'd be y over, or no, y
Move the
minus.
t to the other side to turn it positive. And move the
Okay.
y to the other side because that's where it needs to be.
So it'd be 2 minus y.
Okay. Now, since we have that t, which is the same t, equaling that and also equaling that, then I can just let one equal the other, and I've removed the parameter. And then I can either solve for y or even x. I can do lots of things once I get it to there. But that's how you remove the parameter when you're looking at polynomial equations in t. Okay, it's pretty easy. If you can solve for t, do it with both equations and then set one equal to the other.
Okay.
Now, and in fact, I really don't need to solve the second one. If I solve the first one for t, then y equals, well, what is t? T is 1 minus x over 2. So there's my final equation. Actually, you get to it a little bit better if you don't solve both of them for t. Just solve one of them for t and then substitute. All right, let's take a harder one. One that you can't solve it by solving for t. Take these two parametric equations, and in this case, t is going to go from 0 to 2 pi. Now notice that I could solve it for t, but I end up with t being the inverse cosine of x over 2, and I don't get very far doing that.
Okay.
So there's a special technique you have to do. Solve, instead of for t, solve for the trig function. If this is true, then the cosine of t equals x over 2, and the sine of t equals y over 2. Well, how does that help? Well, I can now square both sides so that I have x squared over 4 equals cosine squared of t, and y squared over 4 equals sine squared of t. How can I eliminate the t? By adding both sides of the equation. In other words, you can always add any two equations. So I'm going to add that to that, and I'm going to add that to that. Well, when I add the right side, what do I get?
Is that 1?
Yes, I've eliminated t. The left side becomes this. What's this the equation of?
Not sure.
The equation of a circle. In fact, it's the equation of a circle at the origin. Okay? But I've accomplished what they wanted, which was to give them, I've eliminated the parameter and come up with this. I didn't do it the same way as I did the first one. Now let me give you a slightly harder one. There's my two parametric equations. And again, I'll let t go from 0 to 2 pi. Incidentally, in that last problem, I get this circle when t traces from 0, remember t went from 0 to 2 pi? Well, there's t going from 0 to pi over 2. There's it going from pi over 2 to pi. There it's going from pi to 3 pi over 2. And finally, in its last piece of its domain, it completes the circle. In other words, it traces a circle in its domain, not twice, but exactly one time. And if you were to put this in your calculator and graph it under parametric mode, one moment. And define t as going from 0 to 2 pi, well, what it's going to do is it's going to graph it, and you're going to see it start there, go there, go there. In other words, you will actually see it trace out exactly one time. Okay. This problem, slightly different. We have a different coefficient. We want to solve it the same way. What's my first step?
Get the identities.
What's my first step, though? That's a very important first step. We know that we're going to end up squaring everything and adding them together in order to get 1. But what do I have to do before that's going to happen? If I were to just square both sides now, I get this. X squared equals 9 cosine squared theta, and y squared equals 16 sine squared of theta. Now I can't eliminate anything. I can't get the sine squared plus cosine squared.
Okay.
So what I have to do before I do squaring is to solve each for the trig function. In other words, if x equals 3 cosine of theta, then cosine of theta equals x over 3. Sine theta equals y over 4. Now you can square both sides and add the two equations together, producing x squared over 9 plus y squared over 16 equals sine squared plus cosine squared, or 1. What's that the equation of?
A circle?
An ellipse.
Oh.
That's the general equation for an ellipse at the origin, where its major axis is 4, its minor axis is 3, and it would trace that way exactly if you were to trace it as parametric equations.
Okay.
So I think that's probably the two most important thing about parametric equations, is what I've just gone over, is how to eliminate the parameter when you have a polynomial type thing, and how to eliminate the parameter when you have it in trig functions. Let's talk about hitting a baseball, because I'm sure you're going to have these problems also.
Okay.
Kevin hits a baseball 3 feet above the ground with an initial speed of 150 feet per second and an angle of 18 degrees with the horizontal. Let me try that. Starts out at 3 feet. Hits it with an angle that is 18 degrees with the horizontal. And the velocity of the ball is 150 foot per second. Will the ball clear a 20-foot wall that is 400 feet away? In other words, there's a 20-foot wall right there. We can predict where that thing's going to come down as to whether it clears the wall or not by using parametric equations.
Okay.
How? Well, remember that the x component of this velocity is what? In other words, if I take this 150 foot per second velocity of the ball and I break it up into its x and y components, what would that be? Use trig.
That'd be tangent of 18.
Now, hold on a moment. What's the trig function that we care about? If I want the x component and the y component, then what trig function can I state? Sines and cosines.
Okay,
What would the
so
cosine of 18 degrees be?
that'd be 8 or x over 150.
Exactly. So x becomes 150 times the cosine of that angle. That's what x is equal to. So if I want the horizontal component, take the cosine of 18 degrees, multiply it by 150, and I've got what?
So -1.
What's cosine of 18 degrees? That's a positive number. And we're going to multiply it by 150.
Oh, I did them together. Okay. So 142.6.
So that's the same thing. When I fire that, or when I hit that baseball at an angle of 18 degrees at 150 feet per second, that's the same as having a horizontal component of 142 feet per second. How about the vertical? What's y going to be equal to? What's the sine of 18 degrees going to be?
Should we do the sine of 18 times 150?
Exactly. That's the vertical component. What is that number?
46.3.
Okay. If we were dealing with forces instead of projectile motion, we could say that if I exert a force of 150 in this direction, it's the same as putting a horizontal force of 142 and a vertical force of 46. In other words, I've broken this thing up into its two components. Okay? So let's take it one step further. How far is my baseball going to travel horizontally?
142 or
This thing times t.
oh.
In other words, it's 142.6 feet per second. Well, how far does it go? It depends on how many seconds you're going. So you're going to multiply it by t, right?
Mm-hmm.
So that's our first parametric equation. X equals 150 cosine of 18 degrees all times t. That's how far it's going to go horizontally as long as it's in the air. Now, vertically it's a little different. Okay? We certainly know the horizontal or the vertical component is 150 sine of 18. And certainly, however long this thing is in the air, I'm going to multiply that by t. But there's an additional factor when I'm talking about its vertical position. You've got not only the vertical component of its velocity affecting where it's going to go vertically, but you've got the force of gravity, which translates to minus 16t squared plus that plus its starting position. So let me rewrite that. So y is a significantly different parametric equation that depends on its vertical component, all times t, and I'm adding 3 because we started 3 feet off the ground. You can certainly see that when t is 0, this would go to 0, that would go to 0. We need to be 3 feet off the ground. We are, by adding the starting height. And this is kind of the standard parametric equation for vertical motion. I could generalize it by writing this, plus its vertical velocity, the vertical component of velocity, times time, plus its initial height. In other words, this is going to be the general parametric equation for the vertical motion whenever you're dealing with parabolic motion. The vertical component, it's always going to be affected by gravity, is that part there, by its vertical component of its velocity, and by its starting height. Whereas the horizontal movement is affected only by the horizontal component of its velocity times the amount of time it's in the air. Gravity has nothing to do with its horizontal motion other than the fact that it's going to put it on the ground sooner than it would without gravity. In other words, it's gravity that causes this ball to fly in that path. But if I want to know how far it's going to go, well, I have to know at what time does the vertical component reach a height of 20 feet. In other words, if I take the vertical component, which is this part here, and set it equal to 20 feet, if I had met y equal 20, I will then be able to solve for t, and I'll know exactly when it reaches a height of 20. Once I have that time, I then plug it in to that part, the x distance, and see how far I'm going to go when the vertical height becomes 20.
Okay.
And if that distance is more than 400 feet, I'm going to clear the wall. If it's less than 400 feet, I'm not going to clear the wall. I'm going to hit it. These problems are usually phrased, where does the ball come down? In other words, let's make it one step less complicated and say, okay, at what distance does the ball come down? Well, I know the height when it hits the floor has to be 0. So I would substitute 0 for y instead of 20. And that would tell me at what, in other words, this is a number, this is a number, the only variable there is t. So this is going to tell me at what time the ball lands on the ground. Once I know that time, I go back to the x-coordinate, plug it in, and I can tell exactly how far the ball is going to travel.
Okay.
That's a typical problem. They also might want to know how high the ball gets. In other words, what is its maximum height? Well, the height is a function of the y coordinate. So I'm going to use this quadratic right here and find its vertex. And once I find its vertex, where on the horizontal axis, at what time will it hit its height? Well, I know how to find vertex. It's minus b over 2a. So I find the vertex of that parabola, and once I find the t that it's at the vertex, then I can go back and substitute it. Well, then I'll know at what time it hits, and then I can plug it in, and I can come up with the actual height. Maybe it gets up to 310 feet in the air. Those are the kind of questions you're going to be asked. Basic ones like that.
Okay.
I would be surprised if they ask you one as hard as the one I gave you, where you have a wall that's 20 feet high. Does the ball clear the wall? That's at least one notch more complicated. Because you're not looking for the ball to hit the ground, you're looking for where does the ball hit the 20-foot height mark.
Yeah.
And notice that if I substitute 20 for y, well, I've got a quadratic. I'm going to come up with two values of t. Well, one of the values is when it hits the 20-foot mark going up. The other value is going to be when it hits the 20-foot mark coming down. So you would take the longer time if you want to know when it hits this 20-foot height. The shorter time is when it hits that 20-foot height.
Okay.
All right, I think that that's probably all of the parametric stuff that you're going to need to know. And they're most likely going to give you the parametric equations, so I'm not sure you have to memorize them. But if you do, x is going to be the horizontal speed times time. That's the x equation. Well, the horizontal speed happens to be the speed of the ball times the cosine of the angle. So it's more complicated to come up with the horizontal speed, but as long as you can take a vector and break it into its horizontal and its vertical components, that's what you're going to need to do. However, notice that, let's see, that was the horizontal speed times time. It's the only thing that affects the x component. The y component is the vertical speed times time minus the effect of gravity plus the starting height. So you end up with a quadratic for the height of the ball at any point in time. And using the two parametric equations in conjunction with one another, let you track exactly what that ball is doing at any point in time, which we would have a hard time doing with just x and y coordinates. We wouldn't be able to do that without parametric equations.
Mm-hmm.
Classic example, I suppose, would be if you were to throw a ball straight up into the air. Well, what's it look like? It looks like this and then like that. You don't get much information, right?
Yeah.
But if you treat it as two parametric equations with time as the factor, then it shows up like this. And now you know the ball goes up. At this point in time, it hits its peak, and then it comes back down. So when you look at it parametrically, you see a lot more information that is valuable. In other words, when I throw it straight up and straight down, I don't see hardly any information at all when I look on the XY coordinate plane. But when I look on the parametric coordinate plane, I know exactly what the height is. That's based on the y equation as a function of t. All right, let's see. Polar equations. Is that going to be part of your final?
Yeah.
Let's review a few things, and we only have a few minutes, so we can't review a lot. But there's some pretty important differences. There's some very important formulas you need to convert polar to rectangular and back. Let's talk about polar. Polar only has two considerations: the length of that and the angle of it. Okay? Well, that looks a lot like our parametric equations, doesn't it? In other words, now you can also lay polar on top of an XY grid. Well, if I do that, what's the x coordinate? There's the y coordinate. What's the trig function that relates everything?
To x and y, or?
Yeah, how do x and y and r and theta relate?
With sine and cosine?
Well, cosine of theta would be what?
X over r.
Which makes x equal to r cosine of theta. By the same rationale, y is equal to r sine theta. So here are your most basic identities to translate between rectangular and polar. There's another one. There's a right triangle there, so I also know that r squared equals x squared plus y squared. And there's your 3 right there. And one last thing that I know is tangent of theta equals y over x. So these 4 things you have to know to go back and forth between polar and rectangular. Let's do an example. Well, we don't really have time. Just make sure you memorize those 3 things that I have circled. Okay. Even though you can figure them out relatively easy by being able to draw that picture. Once you can draw that picture, then you can see that the cosine of theta is x over r, which makes x equal to r cosine of theta. Same thing with the sine of theta equals y over r, which makes y equal to r sine of theta. And then because of the triangle, r squared equals x squared plus y squared, and tan theta equals y over x. So you can figure out all of these as long as you can draw this picture. Okay? And converting is as simple as that. In other words, if that's 5 and theta is 30 degrees, then x is cosine of 30 degrees times 5. So if you were given a set of polar coordinates, you could convert it to x and y quite easily with these 2 equations. If you're given xy equations, you can convert it to polar using the same set of equations pretty easily. So you want to get good at going back and forth between polar and rectangular.
Okay.
And this, incidentally, has that same restriction. I don't know why this book doesn't put this in here. It should, because nothing is better than stating it like this. It's just really, really easy to deal with. It's equal to that only if x is positive. It's equal to the inverse tan of y over x plus pi if x is negative. Same as before. So it's not quite true to say that the tangent of theta is y over x. Really, this is more robust. All right, so your test isn't for a couple weeks?
Yeah, it's
Okay.
um,
I will be prepared to do projecting one vector onto another the next time we meet. So when
okay.
I see you make an appointment, I don't know if you're going to make an appointment between now and Tuesday, but if I haven't heard from you by Tuesday, I'll be prepared Tuesday night to do
Okay.
projecting one vector onto another.
All right.
Okay?
Okay. Thank you.
All right. Talk to you next week.
Yeah.
Bye-bye.
Bye.